All right, good afternoon, everyone. As Dr. Cohen said, my name is Jared Geyer. Just to give you a little bit of background, I've been in the National Weather Service for, it's good to do these talks, actually stop and think, because normally I don't stop and think how long it's been, like 18 years, I guess, so time flies. I went to Valparaiso University, got my undergrad degree there, started in the Weather Service. Immediately thereafter, was a couple years in the National Weather Service office in La Crosse, Wisconsin, about 3 years in Hastings, Nebraska, and then I've been at the SPC since 2003. So it's amazing how much things have changed science-wise. You don't really see the incremental changes day to day, week to week, year to year, but it is amazing, you know, even just the duration of my career, how much has changed technology-wise, science-wise, that type of thing over that time period. So today I'm here to share with you about a couple of topics that have caught my eye over the last decade or so. And some of this is I definitely tend to be motivated by topics that are a little more tricky, or ones that I or we corporately get burned by, that type of thing. And I think overall we've improved our understanding a fair amount in these regards. But I'm going to share kind of some hybrid type topics from somewhat different approaches, different studies that I've done, but yet there's a commonality between them. So I'm going to talk today a fair amount about cool season severe weather environments. Now that'll especially involve the southeast United States, but also weak Cape sort of scenarios. Perhaps not the typical scenarios that we tend to see here in the Southern Plains, particularly in Oklahoma. So we'll start off here with a little interactive exercise. This is, I'll give you a scenario where you can pick between an A and a B type of situation. So I'll show you a couple of soundings, and basically I want you to basically take a look at and see which one you would hedge your bets, so to speak, if you had to pick an environment that was conducive for strong tornadoes. So there's A versus B, A on the left, B on the right. There's, see, corresponding skew T diagrams based on these soundings. There's sounding A, sounding B. If it's a little bit hard to read, mean mixed layer Cape about 2,600 in this sounding. This sounding on the right about 800. You can see the hodograph here for sounding A, and wind strongly varying with height. Upwards of a little bit weak there, around 6 kilometers, but immediately above that, 40 plus knots as you go on up. Sounding B, a little more, not as pronounced of a low-level hodograph, somewhat more unidirectional winds above the near surface layer. So anyone want to go out on a limb and pick A or B? A, okay. How many people would hedge their bets on A? Does anybody want to go B? Only Dr. Cohen, he raised his hand. He's going B. Well, thank you for saying A. I appreciate you guys. So sounding A is our typical plain sounding. Basically, this is from 2011, May 19th is the case. There's the corresponding tornado watch. By and large, that ended up being a blue sky tornado watch of sorts, where in essence this turned out to be more than not a null sounding. Really, basically storms didn't develop, so it was more of a null case than not. There's the corresponding storm reports for that day. Basically reports up in eastern Colorado, Kansas. Nothing happened, frankly, in the tornado watch down across Oklahoma. Why that happened, etc., is well beyond the scope of this talk. So if it wasn't sounding A, it was actually sounding B. And here's some other observed soundings from this day. So these are observed soundings. These are as proximity as you can get. They're not perfectly timed or located, but they're not within. They are within reason of what we typically call proximity soundings, etc. So actually, there were multiple strong tornadoes, in essence, associated with that prior sounding that I showed you. There are actually multiple strong tornadoes, including an EF3 with 2 fatalities in parts of the Carolinas. There's the 3 sounding locations that I showed basically from, these are the available North Carolina and South Carolina soundings. These were for a matter of hours really. Offhand, I think it was 3-4 hours ahead of the strong tornadoes, not more than 6 hours. And there's the GSO sounding. There's Morehead City across coastal North Carolina, and then Charleston, South Carolina. Obviously not very eye-catching in terms of buoyancy. In terms of these observed soundings, the most unstable ones is Morehead City profile, 1,200 or so, EML Cape. Lapse rates are not terribly oppressive aloft. Mid-level lapse rate's pretty weak. Shear's kind of unidirectional, but yet we end up with strong tornadoes, even tornado fatalities. So kind of show this example to kind of set the stage of some of these topics that, that we'll be discussing. I highlight another pretty prolific historical event, the so-called Enigma Outbreak. This is from February 19th of 1884, so just a few years back. But this is, in a historical sense, actually one of the more prolific outbreaks on record. John Finley, famous, one of the initial tornado researchers. There's some discrepancy about how many fatalities there were, but probably a conservative number that Finley came up with was about 800 as far as the death toll. Number of injuries may have even been 2,500. Homeless, 15,000 people. Obviously, a different, a different era, obviously, and communication, and a lot of word of mouth, that type of thing. But a prolific super outbreak type equivalent, and then some, from the late 1800s, focused across the southeast United States. So to kind of get into some of the environments, kind of follow up on my perhaps not too fair comparison. Again, thanks for playing along on the A versus B. That worked out well. So to get into some of these cool season type environments, what I'm showing you here is a plot of ML Cape versus 0 to 6 kilometer shear. To set this up, this is basically looking at information that's equivalent to our mesoanalysis data information. So if you look at what's on our mesoanalysis page, looking at environments, this is basically the same thing in a archived, historical, gridded type sense. So basically, you can think of this as mesoanalysis data associated with reports. In this case, this is mesoanalysis data that's associated with tornadoes, but I've limited it to the cool season. So basically, when I say cool season, you can roughly think of that as November, February timeframe, give or take a month up to interpretation. But in this case, I've got November through February tornado reports. So ML Cape on the x-axis, 0 to 6 kilometer, basically deep layer shear on the y-axis. And I think what most prolifically stands out to me is just notice how many of these tornado events, there's scale on the right in terms of report counts, or basically the tornadoes in this case. Notice how many of these were associated with not only ML Cape of less than 500, but actually 250. And so if you combine the numbers here, it's over 1,100 cases of total 2,200 reports. So roughly half of these, in this particular sample, roughly half of these tornadoes were associated with ML Cape less than 500. Again, not something we would typically think about in Oklahoma. I assume most of you have chased at least some in here. Yeah. You're probably not going out on days when the Cape is 500 or so, right? And that's understandable. And I should say up front and caution that I'm not necessarily. I don't want you to take away from this that I'm not contending that the atmosphere is really any different in other parts of the country, but the way those ingredients kind of come together, the relationship, the balance of those ingredients can come together a little differently. It's not to say that tornadoes don't need buoyancy and this type of thing. It's just the relationship, compensating, offsetting type factors come together a little different. In other parts of the country, different types of regimes, etc. So the main highlight of this is just how much or how relatively little Cape you can get to have tornadoes. Now, is it a little different story with stronger tornadoes, F2 and greater, EF2 and greater? It is to some degree. So this is the same thing, November through February, so basically cool season tornado environments. This is constrained to SIG tornadoes, so basically EF2 and greater. Now you will notice, let me page back and forth, you will notice a little higher number of cases with more CAPE. Still, if you just kind of eyeball the more bolder, brighter colors, if you will, still we're not talking about that much CAPE, again, especially as compared to plains, April, May type cases. There's a large number of these cases, over a couple hundred of them, over half the data set, where the ML CAPE is less than 1,000 joules per kilogram. So again, just trying to kind of raise your awareness that, especially in these types of regimes, these cool season tornado events or even outbreaks that we get again, most of these materialize, say, in the Gulf Coast region, southeast quadrant of the United States. It really doesn't take a whole lot of buoyancy to get even prolific types of tornadoes. So some of this all stemmed from a study that we did, just kind of looking at initially some very basic looks and examinations at some of these events, some of the patterns, the commonalities of some severe weather outbreaks in the southeast United States during the cool season. So in this initial study that we did, frankly, it was about maybe a decade or so ago, we'd found that 68% of all December through February was the time frame that we looked at. Or excuse me, that's a Galway finding from his study back in 1981. Basically, 68% of all December through February tornadoes in the U.S. occurred in the southeast. Noted that cool season conditions, deep layer shear, favorable wind shear is common. However, instability seems to perpetually be the main question. Is there enough moisture? Is there enough instability given environments? Just given the typical strength of the wind shear and forcing, for that matter. Overall, is there enough moisture and instability to have supercells and tornadoes? And again, noting there that the moisture and instability seems to be the key question in a lot of these cases. But again, from what I showed you, just taking those prior plots for on their face value, really it doesn't take a whole lot. It's just need to generally have just an adequate amount. It seems like in a lot of these cases. So the study we looked at mid-October through mid-February time frame. We'd examined 20 seasons from the mid-80s onward. And for significant tornado, so when I say that, or strong tornadoes, basically I'm talking about F2 or EF2 or greater. And our focus was on non-tropical systems. So we were going after, more cool season, not the August, September-ish, or even into October tropical sort of systems. So this is just a plot of the tornadoes that are incorporated into our study. Again, strong tornadoes, EF2 or F2 and greater. In all, the study incorporated 239 F2 and greater tornadoes. You can see the corresponding F-scale breakdown there on the bottom. And it encompassed 100 tornado days conveniently. Tornadoes by time is kind of an awareness thing that I wanted to share with you. Not a big deal, but certainly something to be aware of when you go into if you're pinning what your future careers are, whether it's as operational forecasters or if you have interest in social science realm, vulnerabilities, this type of thing. This kind of gets into the vulnerabilities of the region where a lot of the tornadoes that happen during the cool season, there's a somewhat higher tendency for them to occur into the evening, late at night, or even in the early morning hours. Much, much, much more common than we have here. It's pretty unheard of. They have happened historically. You can get, late evening, overnight tornadoes here, but comparatively much rarer than basically the southeast United States, anywhere from mid-south, say roughly, Arkansas, Louisiana, eastward. A lot higher percentage of tornadoes can and do occur. Even, again, these are strong tornadoes. So you think about vulnerabilities late at night, people sleeping, higher percentage of mobile homes, that type of thing. Certainly, it can relate to vulnerabilities and especially when we're dealing with stronger tornadoes. So there's actually a relatively high percentage, a fair number of these cases that occur, say, anywhere from 2Z to 10 or 11Z. Certainly a very low percentage of them, say in the 12 to 15Z time frame, but compared to what we're more used to seeing in Oklahoma, threats that increase a little bit earlier, say in the late morning or early afternoon time frame, and then a longer duration type of vulnerability into the overnight hours, certainly. So our methodology in terms of looking at these events was we'd use NAR, North American Regional Reanalysis data at 6-hour intervals to kind of get an idea of the overall patterns, that type of thing. We also use proximity soundings. If we were doing this study now, it would look a little different, but we had to go with some of the best data, or some of the data, or what data that we did have available. And so that included, some of the details there included 57 proximity soundings amongst 50 tornado days. So it wasn't a perfect matchup, data availability of soundings and NAR data, et cetera, but kind of did the best with what we had to work with at the time. Just kind of idea in terms of looking at the overall patterns. Basically, we constructed these web pages to kind of at least make subjective kind of cursory looks at the overall patterns, that type of thing, and also the reports, and kind of sync that up with the timing of the reports and where that occurred in relationship to, say, 300 millibar, 500 millibar features, trough locations, that type of thing, wind speed maxima, etc. And just as an example, 500 millibars here, we found that over 70% of the cases were actually associated with kind of the anticyclonic southern fringe of a mid-level jet. There's an example there on the left-hand side. And a smaller portion of the cases actually coincided with more kind of the nose of the mid-level jet or beneath the jet axis. And really, by and large, it didn't seem like the actual strength of the winds didn't really discriminate between whether it be more isolated events or more prolific, larger outbreaks. I think that was much more of a function of moisture and instability from what it seemed like. So some of the data from some of the proximity soundings. So these are box and whisker diagrams. Basically, the box is middle 50 percentile values. The whiskers on the end are the outlying, the outer 10% values. Surface dew points, something basic. We're probably a little, maybe as a, this might be heresy, I don't know. Maybe we're a little too buoyancy or cape focused at times. Maybe, at least the way my mind works, sometimes I find it a little bit easier to think about, just the raw low-level dew points, primarily surface dew points or even 850 type dew points. Obviously, cape is much more of a, is a function of more than just beyond surface temperature and dew point, but obviously there is a correlation, but yeah, it's also reliant upon above that, above the boundary layer, that type of thing. And I think just being mindful of surface dew points, availability, that type of thing, I think is a little less maybe nuanced than cape can be at times. Obviously, you can have cape profiles that are wider, fatter, especially like we see this time of year in the plains, versus skinnier capes. So what I'm getting at is not all, say, 1,000 joule per kilogram capes are created equal. There's definitely differences in terms of parcel accelerations, that type of thing. So the quantity matters, but yet it's kind of distribution, the profile of the cape, etc. But anyways, here's surface dew points on the left-hand side of the diagram. If you're looking for upper 60s, strong upper 60s to 70 plus dew points in the southeast during the cool season, you're not going to see it. Again, these are strong tornadoes, so it's you can see a fair portion of those cases, upwards of, say, 50% of them are occurring with dew points of mid-60s or lower. There's even some cases upper 50s dew points, that type of thing. Obviously, dealing on the right-hand side, this is the mean relative humidity, basically just showing us that we're dealing with pretty moist profiles by virtue of the relative humidity there from the LCL to the LFC. So moist profiles. Mid-level lapse rates aren't going to be strong. A lot of moist or approaching moist adiabatic type of looks to a lot of the profiles. And here's CAPE on the left-hand side of the diagram. Most unstable CAPE, ML CAPE in the middle, and then surface-based CAPE. Somewhat similar to maybe what I showed on the prior diagram in terms of the plot of strong tornadoes. Now, they're a little different data sets. These are observed soundings and modified at that. So a little bit different look than some of the gridded information that I showed earlier. But basically, the overall theme is still that you're not looking, especially using a spring Oklahoma type standard, you're not going to be seeing high-end amounts of buoyancy. There for ML CAPE, for example, 870 to basically 1,700 joules per kilogram is the 50 percentile values, the most common values associated with strong tornadoes across the Gulf Coast region, again in the cool season time of year. One thing that's even though you do see a rather wide disparity of CAPE values, again, if we were comparing this to May tornadoes in Oklahoma, this would be probably 2 or 3 times what we're showing for ML CAPE. But one thing that's more of a commonality is if you look at more lower integrated values of CAPE. If you look at, in this example on the right-hand side, I have 0 to 3 kilometer ML CAPE. Those are going to look much similar. So if you looked at these cool season environments, ML CAPE, as compared to Oklahoma, they're actually going to look relatively similar. So there seems to be something to that maybe more lower concentrated type of buoyancy, relating to partial accelerations, et cetera. So what I'm getting at is the disparity of CAPE is not as high if you look at, kind of a smaller portion of the overall buoyancy layer, et cetera. Okay, getting into aspects of shear, so deep layer shear or shear overall on the left-hand side, deep layer shear on the left-hand side of my left diagram. Very strong shear, the mean values upwards of 50 knots or a little bit higher. So deep layer shear is strong, as we said in a lot of these cases. 0 to 1 kilometer shear, perhaps, kind of do more Oklahoma spring comparisons. For tornadoes around here, we might only be seeing, say, 15 knots, 20 knots, 0 to 1 kilometer shear, something like that, as a kind of a minimum, especially as we get deeper into the year for tornadoes. Certainly much higher in these cool season Gulf Coast cases where you may have upwards of, say, the upper 20s into the 30s or even higher in terms of 0 to 1 kilometer shear. Here's SRH on the right-hand side. Same theme, basically relatively strong values of 0 to 1 kilometer SRH, 0 to 3 SRH as well. Okay, some of the composite parameters, obviously, it's certainly an operational SPC environment. We look at these, we always caution that it's good to know the constituent values that go into these parameters. And one thing I'll point out is that CAPE is a pretty important constituency value, especially when you get into STP. So what do you think is going to happen if your CAPE isn't overly high in the STP? I think it would stand to reason that your overall STP is not going to be all that high. So we'll show that here, especially on the right-hand side of the diagram. So again, these are strong tornadoes, cool season southeast United States. And basically the STP values there associated with these strong tornadoes are, in some cases are less than 1. So there's the couple of different calculations there, but basically the mean values were 1.5 as far as STP goes. Certainly some cases where you get upwards 2, 3 or more, but there are a lot of cases, kind of a scary number of cases. Again, these are strong tornadoes where they're occurring with STP values below 1. That's not to say that doesn't happen in the plains and deeper into the year, but certainly it's more of a commonality to have low STP values. It's not a knock on the STP, it's just being mindful of some of the constituency dependencies that go into the STP calculation. So Southeast cool season summary, kind of basically a summary of what I showed you so far. Basically kind of confirm the prevalence of high shear, low cape sort of regimes for Gulf Coast F2 and greater tornadoes. Again, usually dealing with relatively strong values of shear, 0 to 6 kilometer shear, basically 45 knots or greater was kind of a common thing. Noted here, strong 850 to 925 millibar winds, basically strong winds, the lowest 2 to 3 kilometers above ground level. 850 millibar wind speeds, typically 40 knots or greater. 0 to 1 kilometer bulk shear, typically greater than 20 knots. Low dew points, mixing ratios, basically anything related to moisture appears to be paramount for anticipating these cases. The final note there is just a re-emphasis that total CAPE can be relatively modest, especially compared to our spring environments in the plains. It seems like the concentrated low-level buoyancy is likely, at least from a recognition type sense, is perhaps another way to look at it, indicative of sufficiently warm, moist, low-level profiles that are sufficient excuse me, for tornadoes, even strong tornadoes in some situations.